Hello, everyone. Welcome to the e-learning space of data science for public policy. This video is brought to you by the DSPS Data Science and Policy Studies program under the Chinese University of Hong Kong. This video is supported by the CUHK Courseware Development Grants Scheme. Our topic for this video is about correlation. We're going to have a revision on what is correlation, then we're going to do some applications through data. First of all, correlation refers always to a linear relationship. So if x and y are a pair of random variables with mean mu x, mu y, and variance sigma squared x and sigma squared y, then the population correlation coefficient would be covariance of the two random variables divided by the product of the standard deviation of x and standard deviation of y. So here we can see this is a little p here, which denotes the population correlation coefficient. So this little p is called rho, RHO. So the rho equals to covariance of the two random variables divided by SD of x times SD of y. So for sample correlation coefficient, so instead of two random variables, if we're talking about two samples, so the formula is pretty similar, but we denote this sample correlation coefficient as R, and then we're going to compute this kind of summation values. But if we use data, we don't have to calculate it by hand. So I'm going to show you later on how to calculate the correlation coefficient using data. So now move on to the very bottom picture. Then we can see at the middle, when there is no correlation, the rho or R equals to 0. That means that for x and y, which is the x-axis and y-axis, so the dots are scattered all around. So there is no clear direction on where the dots are pointing at. So this is called no correlation. So this is you can see a random pattern of all the data points. And moving to the very left-hand side, we can see perfect positive correlation. So although this usually won't exist in real life, but if your correlation equals to +1, that means when your x increases, then your y increases together perfectly. So you can see the data points all unified, pointing to exactly one direction. And then on its right-hand side, we can see high positive correlation when rho or R equals to 0.9. Then here we can see the dots are still pretty close to each other and they're pointing to one direction, but the data points are a little bit scattered, a little bit more compared to the perfect positive correlation. And moving to the right, we can see low positive correlation. So when your correlation coefficient decreases or going more closer to 0, then your data points is going to be more farther from each other. And then to the right-hand side, we can see for low negative correlation, high negative correlation, and perfect negative correlation, the picture, the story is pretty much similar. So when your correlation coefficient is more closer to 0, then your data points is going to be more scattered. But here, the biggest difference is that when there's negative correlation, then the direction would be different. So when your x-axis, the value increases, then your y is going to be decreased. So this is how we interpret the correlation coefficient. A positive correlation means that larger x are associated with larger y, or smaller x are associated with smaller y, and vice versa. And for negative correlation, that means that larger x is associated with smaller y, and vice versa. So again, please remind that for rho or R, their values are going to be always within a -1 to +1. So how to verify whether two random variables are correlated? So we can do a hypothesis testing. So we are going to test the hypothesis of no relationship between a pair of random variables in the population. So first, we can set up a null hypothesis, H0, that H0 means rho equals to 0. So again, remember, when your rho or your R is 0, that means there is no correlation. So we're going to set up a null hypothesis saying that there is no correlation. And then versus a alternative hypothesis. So if you do a single tail test, then we are going to set up a HA, which is rho larger than 0 or rho smaller than 0. But if you're going to do a two-tail test, then your rho can just be simply not equals to 0. So when it's not equal to 0, that means somehow the two random variables are correlated. And after we set up the hypotheses, then we're going to do a test statistic. So that means you calculated a t statistic, and then this is going to follow a t distribution with n-2 degrees of freedom. So the degrees of freedom is n-2. And after you calculated n-2, you can look up to the table and check the t critical values and to determine whether you should choose your null hypothesis or your alternative hypothesis. So moving to the application part, again, we are going to use the Hong Kong visitor arrivals sample data from the Hong Kong Tourism Board. You can download the Excel file from the DSPS website, or you can look back to the very first e-learning video to see how we get the data. And today we're going to use two variables, which is the total VA overnight and the total VA same day. So total VA overnight refers to the visitors who stayed overnight in Hong Kong versus the total VA same day means the visitors that come to Hong Kong and leave Hong Kong on the same day. So they're not going to spend their night at any hotels in Hong Kong. So first of all, in Stata, we have to load the data set into Stata. So you have to import Excel, and then you type the path, the computer path, which is where your Excel file is located in your local computer. And then next, we're going to TS set time. So the file has a time variable, and we have to let Stata recognize that this is a time variable. And then we're going to create a variable called period, and period has 3 different values, which is 1 normal times, 2 EBIL times, and 3 COVID-19 times. So again, if you're not familiar with it, you can look back to the previous e-learning videos, which I explicitly talk about how to set up or create a period variable. And then moving to the main dish of today, so we have to calculate the correlation using Stata. So how? So first, in the first line, you can see there is a star correlation. So a star means that this line Stata is not going to recognize this as code. So this star and then you type correlation is just a text reminding yourself that I'm doing a correlation. So you can type anything you want, and Stata is not going to run this line of code. So Stata is going to run the second line of code, which is the PW core, which is the Pearson correlation, PW-CORR. And then we're going to put the 2 variables of interest, which is the overnight and the same day variable, comma, and then we put star 0.01. So this means if the correlation is significant at 1% level, then please put a star next to it. And then we're going to have this small table down here. So this table, the important part is the 0.9702. So think of this as a 2 times 2 table, where each variables appear in both the head column and the head rows. So 0.9702 refers to the correlation between the 2 variables. So here again, it's very close to 1, and this is a very high positive correlation. And then there is a star indicating that it is significant at 1% level. So this is a very high positive correlation. And then if you want to visualize the data, you can type 2-way and then indicate the plot type scatter, and then put your y variables and your x variables. And then after you close the bracket, we have another bracket, which is the LFIT CI. Again, it is discussed in the previous video, but LFIT CI is basically talking about the linear fit line, the red line down here. So here we can see down here we have some data points that they're very close to each other. And then after we fit a linear line, then we can see that all the data points are pointing to one direction. So as x increases, y also increases. And then next, if we want to only look at period 1 normal times, then we can again do pwcore, the correlation command, and then we calculate the correlation coefficient. And here we're only using the data that is during period equals to 1 normal times. So now we can see the correlation coefficient is 0.7473. Still there is a star, that means it is still significant at 1% level. And then when we plot a scatter plot, then here, of course, the data points is going to be fewer because we're only looking at certain periods instead of all the times. And again, the syntax of plotting the graph is that you just have to add if period equals to 1 normal times. So this is going to limit your data, and your LFIT CI is going to be only focusing on data points that is for period equals to 1. And then here we can see down here in the graph, the data points are a bit more far from each other. They're not that crowded. And then somehow some dots are quite far from the fitted line, the red line. So here we can see, but they are still pointing to one direction. And you can see there is a still clear relationship that when X increases, Y also increases. So next, if we're only looking at e-bill times, the expedition bill times, then the correlation is 0.9444, and then with a star, so it's significant, and it is also very high because it's more than 0.9. And then if we plot the two-way scatter plot, then we can see there is still a fitted value showing that when X increases, Y also increases. But now since we only have a few data points for e-bill times, it's a very short time. So when your data points is not as many, you have to bear this in mind to see whether it's a good conclusion. And then lastly, if we want to look at the correlation for period equals to 3 COVID-19 times, then again, up in the table, we can see the correlation coefficient is 0.9794 with the star, which is very high and significant. But if we plot a scatter plot, we can see that most of the dots are located in 0. And then there is only 2 dots located close to the fitted line. So here again, based on the fitted line, we can also see a clear relationship that when X increases, Y also increases. So that is going to agree that it is a positive correlation. But the data points again is quite few along the X and Y axis. So this is also something to bear in mind. So this is basically everything, and I hope you enjoyed this video. Thank you.